All right, so in our last class, we finished off with precipitation reactions, where we just scratched the surface. The whole idea being that we're mixing two soluble solutions. They come together and they form a solid, and that solid falls down to the bottom of the container. So what we did last time, we started by identifying the products and which of those products will be a solid or the precipitate. Okay, so we looked at initially the sodium chloride reacting with silver nitrate. And when that reacts, it forms sodium nitrate and silver chloride. And we use this sort of a pseudo Punnett square to figure that out. Or if you're really good at this stuff and it comes easy, you can just swap the cations and anions, and that shouldn't be a problem. Okay, so the next thing we did is we went and looked at our solubility rules. And we know that these solubility rules are in order of importance. So the rule 1 supersedes rule 2, supersedes rule 3, etc. And from that, we were able to tell that given these rules, right, sodium nitrate based on the first rule should be aqueous, and silver chloride based on the third rule, where silver is an exception to the chloride salts rule, that should be our solid, that should be our precipitate, okay? And so we get our aqueous sodium nitrate and our solid silver chloride. And we did a quick example with another reaction where we had lead nitrate and potassium iodide. And we found that the not potassium iodide, the lead iodide should be the precipitate based on the solubility rules, the same procedure. What was that?
We can't see the lecture slides.
You can't see the lecture slides? What?
I can't see the lecture slides. I don't know if it's just me.
I can't see it either.
Yeah, we're still on the screen with the submission of the lab. I think you need to change your screen.
Thank you. Unfortunately, yeah, so let's try share. Aha. Thank you for letting me know that, because that's something. There we go. That should do it, hopefully. And then from here, there we go. Okay. There we go. Again, remember, new to me. So thanks. You got to let me know these things because I don't have your view. So thank you. I appreciate that. So we went through this. We had the sodium chloride and silver nitrate, right? Those reacted. We had that pseudo Punnett square. We found the sodium nitrate and silver chloride were the products. We used our solubility rules to get us there. And we found that sodium nitrate is soluble and silver chloride is insoluble, meaning that silver chlorides are precipitate. We did the same thing for lead nitrate and potassium iodide, where we made lead iodide and potassium nitrate. So something that's important here is, again, knowing your nomenclature rules, making sure that you can figure out the chemical formula from the name. And so knowing your polyatomic ions, again, extremely important. And as is knowing things like the type 1 and type 2 ionic compounds, especially for these precipitation reactions. Okay. And so we kind of left off there. We identified our products and we identified which of those products is the precipitate. Then we left there so we could start our next section, which is actually describing these reactions in a solution. And so what's happening here, remember we have two aqueous solutions that we mix together. And so both of the reactants are always going to be aqueous. And we're identifying first and foremost, what are we making, right? And then the phase of that thing that we're making. But there are different ways of describing these precipitation reactions that give you different types of information. So what we just did, the chemical equations that we looked at last time. So you see here and here, right? Oh, by the way, thanks to Vincenzo, I actually have ordered a pen to hopefully help with the writing on here. But because of Amazon's issues with labor, I'm not sure when it'll get here, but hopefully soon. Hopefully it'll be here today, and by tomorrow I'll have better writing on the screen here, but we shall see.
Awesome.
So, Professor, I have a question.
Yes.
You're not recording this, but are you going to put this in YouTube?
Yeah, I am recording it, and I'm just to put it all on YouTube. Yes. Right. Yeah, and I'll send you guys the link as soon as I get those up and running properly. Okay. So the chemical equations that we did last time, where we just had everything was in terms of the chemical formulas, the full chemical formulas, for those two examples, those are called molecular equations or formula equations. Different resources will call them one or the other. I tend to use molecular equations based on the majority of resources that I've learned from. But I think our textbook may occasionally call them formula equations as well. Same thing. Okay, so they show basically all of your reactants and all of your products in their complete molecular formulas, which isn't exactly how they exist in solution. And so in order to show how they exist in solution, because that's part of understanding what's going on in the reactions of aqueous solutions, is understanding that you have, if you have an ionic substance that's soluble, it is dissociated into its component ions. And so with that in mind, we have a couple of different ways of describing the chemical reactions. And those are the total ionic equation is the first one we'll look at. And then the net ionic equation will be the second one that we look at beyond the molecular equation. So we'll have three ways of looking at it. So if we take that first chemical reaction and we basically look at sodium chloride reacting with silver nitrate to form sodium nitrate and silver chloride. To get the total ionic equation, essentially what we're doing is we're taking that sodium chloride that's aqueous and we're breaking it apart into its component ions, because when it dissolves, right, those two ions, they break apart, okay? And so in solution, it exists as separate ions that are solvated by the water. And so does the silver nitrate, right? So we write that. Anything that's aqueous, we show it, if it's an ionic compound, as dissolved, as broken apart, right? Like we described ionic substances when they dissolve in water, okay? And so you'll have sodium ion that's aqueous, chloride ion that's aqueous. You'll now have silver ion that's aqueous and nitrate ion that's aqueous. And all of these, remember, the idea for this reaction that we're describing is when you have the reactants, it's when you initially mix them together before any reaction takes place, they mix together and all of these ions are what are in solution. When it comes to stoichiometric coefficients, we'll see that in an example in a minute, okay? When those reactants react, they form sodium nitrate, which is aqueous, and the sodium nitrate, since it's aqueous, it will exist in its dissociated form. So the sodium ions will be separate from the nitrate ions. But then the silver chloride becomes a solid. Now, when it becomes a solid, it means those silver and chloride ions are stuck together, right? They aren't dissociated, so you write them down as if they are stuck together, forming that solid. And that solid is what, when it gets to be a big enough mass of solids, ions stuck together, it precipitates, it falls to the bottom. And so the idea of a total ionic equation is you're showing everything that's in the solution, right? But when you do that, you're showing sort of as the reaction as the reactants form products. And so you see how it is before, how it is after, and everything is written down, okay? So when it comes to the products, right, just keep in mind, anything that's aqueous, you're gonna make sure that it's dissociated, right? So if you will, sodium nitrate's aqueous, so you're gonna write those component ions. But if it's a solid, it's gonna stay together because that's how it exists. And so that's what that total ionic equation is showing. The net ionic equation, right? So the net ionic equation is a little bit simpler because the net ionic equation just shows you the actual reaction taking place. So in this reaction, the things that are actually reacting are the silver ion and the chloride ion, right? Those form the silver chloride. That's the actual reaction that's taking place. But if I go back to the equation, the total ionic equation before, you'll notice that sodium ion here and sodium ion there look exactly the same on either side of the arrow. So does the nitrate on one side and the nitrate on the other side, okay? Those two ions. So the are called spectator ions, right? So these spectator ions, those are ions that are in the solution. They're not involved in the reaction, okay? And so those spectator ions are just, you just list them. You don't have to list stoichiometric coefficients. You have sodium plus and, right, nitrate, NO3 minus, right? And those, they're not involved in the reaction. And so when we look at the net ionic equation, it just sort of simplifies things. It gets the things out of the chemical equation that aren't actually reacting. They're still in the solution. We just don't write them when we look at the actual reaction that's occurring. Okay, so those are the three ways that we can write out a chemical equation for a precipitation reaction. We have the molecular equation, which just shows everything as chemical compounds using the whole molecular formula. Then we have the total ionic equation, which shows all of the different components of the reactants and components of the products as they exist in solution. And then you have the net ionic equation, which just by itself describes the reaction. And so if we take and look at the reaction that we used last time, the lead nitrate reacting with potassium iodide. So in our previous example, we found that produces lead iodide, right, and potassium nitrate. Okay, and so we have a balanced chemical equation from this. That's an important aspect of this, right? When we balance it, we need to make sure we have the same number of ions on either side of the equation like we've always done. But now, when we write out the total ionic equation, we're going to have to take into account stoichiometric coefficients as well as subscripts, right? Now, when you have a polyatomic ion, right, so this nitrate here, that nitrate stays intact. This subscript for the nitrate says that there are two nitrates. So you have two nitrate groups, right? One nitrate and a second nitrate. And those two nitrates are attached to lead until they go into solution and form an aqueous solution. So with the total ionic solution, those two nitrates break apart from the lead ions, and they leave you, as we'll find with anything that's aqueous, it'll leave you with lead. So we have our Pb2+, right? And this is lead 2. We know it's 2+ because of it's in the new form or the standard form of nomenclature for type 2 ion. And that lead 2+ is going to be aqueous, okay? But then since we know that it breaks apart into a lead ion with a 2+ charge and two nitrates, right? You have two nitrates, this subscript out here becomes the stoichiometric coefficient because it's broken it apart. You've broken it into two pieces. So now you have 2NO3 minus, that's also aqueous, okay? Plus, now you have a stoichiometric coefficient in front of the potassium iodide. That's going to apply to both the potassium and the iodide, because if 1 mole of potassium iodide dissociates into 1 mole of potassium and 1 mole of iodide, then 2 moles of potassium dissociate into 2 moles of potassium and 2 moles of iodide. And you'll express that using stoichiometric coefficients. So 2K plus aqueous plus 2I minus aqueous, okay? And for this, I'm going to have my arrow here. Now I'm going to make my products. And for this reaction, I'm going to start my products down a little bit lower so that I have enough space. But when we have the solid, anytime you have a solid here, it stays intact, right? So when we write out that total ionic equation, the solid is going to stay a compound. So this is going to make lead iodide. Oops, I don't need the parentheses there, so I'm going to erase that. There we go. And that is going to be solid, right? So anything that's a solid or a liquid in this chemical equation, or a gas, those stay as solids, liquids, or gases. Anything that's aqueous is what's going to dissociate into its component ions. So now we go to our potassium nitrate, and put that in, again, that stoichiometric coefficient, the 2, applies to both the potassium and the nitrate. So this will be 2K plus aqueous plus 2NO3 minus aqueous. Okay? Now, on this one, we've got spectator ions to identify as well. And generally, when you're doing the total ionic equation is the best time to identify those spectator ions. And so here, the potassium ions are the same on either side of the equation, and the nitrate ions are the same on either side of the equation. So if you identify those spectator ions now, then it's really easy to go to the next step of writing in the net ionic equation, where you just take the ions that are left over, and sort of by convention, we're going to write the cation first. Okay, so here we'll have our lead. It's aqueous, plus, again, we need to make sure this is a balanced chemical equation. Every time we have a chemical equation, it should be balanced. So here we just take the 2 iodides, and that should react to form our lead iodide solid. Okay? And so that's how we're describing these chemical reactions in the solution based on these 3 different types of chemical equations, right? We've got, again, the molecular equation. Okay, so we got the molecular equation, shows all of the chemical compounds in their full chemical formulas. The total ionic equation, which shows everything that's in the solutions in its form initially, and then how it exists after it reacts. And then the net ionic equation just shows the actual reaction that's taking place. Okay, any questions on that so far?
Yes, I have a question.
Mhm.
So the way I was doing it, it was I would look for the solid, and then so PbI2, and then from there I would work backwards and just see what makes that solid instead of doing it the way you did it. Is that okay to do?
You mean by identifying the spectator ions?
Identifying for the net ionic equation. So I would say, okay, if the answer is PbI2, then I would look for Pb and then I, and then everything else is a spectator ion.
Yeah, that's the same thing that I did, just sort of the opposite order. But yeah, that works also. In fact, that's how I identified the spectator ions in the first place, right? I looked, and basically, if you do that, you can. So if we go here and say, yeah, okay, here's my lead iodide. That's my solid. That's the thing I'm creating, which means that my iodide and lead are the things that are going to be involved in the actual reaction, and everything else is a spectator ion. Yeah, that's essentially the same thing. So the order doesn't really matter. The process of it, yeah, doing it that way shows you know what's going on. So yeah, that's totally fine.
Cool.
All right. So what we're going to see now is when we do precipitation reactions, we're really looking at stoichiometry of a solution, okay? And so there's going to be this change to stoichiometry in a solution. In the past, when we've done stoichiometry, we've always used a combination of these 3 processes. Remember, when I'm talking stoichiometry that we've done in the past, we're talking about generally how many moles of something or what mass of something that we've had previously. And so what we started with, if we were given a mass, right, we would take that mass, right? So if we were given a mass, we would take the mass, divide by the molar mass, right, in order to get the moles of that product or reactant. Then we would convert from moles of one thing to moles of another using a mole ratio. Now remember, if we were given moles of a product or a reactant in the first place, we wouldn't have to divide by the molar mass because it was already in moles. Then we would multiply the moles of the thing that we wanted to do. If we were looking for the mass, we would multiply that by the molar mass in order to to get back to the mass, okay? So that's sort of just a quick and dirty outline of all of the stuff that we've done before, right? Let's see. Okay, so Jennifer, actually, I've reordered the slides from what I had on what it was posted, I think. So I'm almost there. So thank you for pointing that out. But this time we're still in good shape. So the thing I want to point here is that in the past we've always dealt with a mass. We started with. Try that again. We've always started with. Right, with a mass or moles. And we've always determined, right, or ended with moles or mass. So that was sort of our toolbox for doing stoichiometry in the past. We're going to add something to that here. So when we're using molarity and volume in stoichiometry problems, because now we're dealing with solutions as opposed to just an amount of something. A solution has a solute and a solvent. We're interested in the solute. And so what we're going to do to get to that moles initially, right? Back on this page, right, we said, okay, if we were given a mass, right? If we're given a mass, we would divide by the molar mass to determine moles. Well, to get to moles, that's the first, that's the important thing right there, getting to moles in that first place. So when you have a mass, you divide by the molar mass. If you're given a solution, instead of what you did with the solid, now with a solution to get to a number of moles of something, you have a volume and a concentration, which we learned when we did dilution, right? Volume times concentration is equal to moles. Okay, so we can figure out how many moles of a reactant we have if we know the volume of the solution and the concentration of that solute in the solution. So you multiply those, that gives you moles. And so that essentially is sort of like that first step in the previous reaction, or the previous set of rules for stoichiometry, except instead of mass divided by molar mass, now we're just saying volume times concentration. The next part, right, is the same. Essentially, if we want to convert from moles of a reactant to moles of a product, we use the mole ratio. That's not going to change at all. Once you have that, right, so if you know how many moles of a product you're looking for example, the next thing, if you end there, hey, you end there and you're done, right? And that's why we use some combination of these. It kind of depends on the question. So I've got a couple of example problems to look at in a minute. But those examples might, or problems that you encounter might ask you for, moles of a product. They might ask you for mass of a product, or they might ask you for volume of a product. And so in order to get the volume of the, let's say you have one reactant, you have a volume and its concentration for one reactant, how much volume and concentration of another reactant do you need? Well, that's one of the two ways of approaching this. So in this case, you're in moles of a second reactant, for example. If you want to know what volume of that second reactant you have, if you know the concentration, you can get that volume by, in this case, dividing by the concentration of the solution. So you can divide moles by concentration in order to get the volume of that second solution, okay? The other way to do it is if you're looking, right, if you're looking for the number of moles.
Professor, we lost you for a few moments. Can you just go back? We had like a volume issue, a couple of
Sure.
us.
So I was basically still on the idea of if you have a certain number of moles of a product or reactant, right, you can determine the volume of the solution that contains that solute by dividing by the concentration, and that'll give you the volume of that other solution. Okay. So, all right. Yeah, Yeah, thanks for stopping me. Make sure that that you guys do that. This is one of those things, we're going to run into this quite a bit, I think, as we go through, converting everything to online teaching. I know for my wife's 4th and 5th grade class, they're all going online in LAUSD, and their internet cut out somewhat regularly. There's so many people using Zoom and whatnot. So anytime that happens, make sure, just like you did, stop me and keep going after we get back caught up. Okay, so if you want to find the volume of a second solution, you divide the moles by the concentration, okay? The other thing you can do is if you want to find the mass of say, a product that you make. Well, if you use your mole ratio to figure out how many moles of that product, right? You do the same process that you did for the other stoichiometry problems. Oops, try that again, right? Where you would multiply the moles, right, by molar mass in order to figure out how many grams. And you might want to figure out how many grams you have in a precipitate, right? Because you're seeing how many grams of a solid you make from the mixture of these two aqueous solutions. That's a reason you might want to do it in that way.
Hi, Professor. Sorry to interrupt
Yep.
again. We lost you again for maybe like 5 or 10 seconds.
Okay.
Sorry about that.
Hold on one sec.
When you get to the last bullet, make the slide.
Say that again, Kaylin.
When you get to the last bullet point of the slide where it says multiply moles by molar mass.
Okay.
And then the yellow, that's where we can do it.
Yeah, gotcha. Great, thanks. Yeah, so so the reason you would multiply the mole, darn it, every time I go to that, try that again. Go back here. Okay, so the reason you might take and figure out, let's say you were mixing a solution or two solutions, right? And when you mix these two solutions, you wanted to determine how much precipitate you made by mass. When you mix those two solutions, you can determine the number of moles of product you make, and then you can figure the mass of that product by just multiplying the number of moles by the molar mass. So you might want to know the mass of a precipitate after a calculation, right? So for example, if you were expecting silver nitrate reacting with sodium chloride, you could predict how much product you got based on the concentrations of the silver nitrate and the sodium chloride, and then you could predict the mass of silver chloride that you would produce. Okay, so to look at this, find. All right, so for that, we're going to go ahead and do an example problem. And this is just if you take any kind of a balanced chemical equation, it doesn't have to be a net ionic or a total ionic equation. A molecular equation would work. And you can calculate, for example, how many grams of a reactant, in this case, or will be needed to react with a certain concentration and volume of another reactant. So in this chemical reaction that we have here, right, we've got zinc reacting with hydrochloric acid, right, based on the equation that's listed. And so this asks for how many grams of zinc react with 50 milliliters of 6 molar HCl. And so on this, you're saying, okay, I know how much of one reactant I have, the hydrochloric acid, how much of the other reactant are going to react, okay? And so on this, you start out sort of with what you have, just like we went through in this previous slide, right? Multiplying the volume of a solution by its concentration. And so when we multiply the volume, in that case, the 50 milliliters, but we're going to convert it to liters, right? So 0.0500 liters, because remember, molarity is in terms of moles per liter. So here, we'll start off on the left-hand side, 0.050 liters times 6.00 moles of HCl per liter. And I always write it out, right? The moles per liter. Because if you do moles per liter like that, right, you can see where the units cancel. Okay, so that's the first step. Your liters will cancel out. Then you want to use that mole ratio. In this case, the mole ratio is 2 moles of HCl for every 1 mole of zinc. And from that, it's a pretty simple calculation, right? You just plug it in and make sure I've got that. You come up with 0.300 moles of zinc. Okay? And so that's the first step. And then once you know how much zinc you have, it's the same type of things that we've done in the past, right? If I want to know the mass, I take the moles, so 0.300 moles of zinc, and I multiply by that molar mass, so 1 mole of zinc. And just as a reminder, the periodic table that you're going to use, so I'm going to go.
Excuse me, sir. Can I? Sorry for interrupting.
No. That's what I want you guys to do when you have questions.
Thank you. That's 0.3 moles zinc that you just wrote. Is that calculation of 0.05 times 6 divided by 2?
Oh, maybe. You're absolutely right. That should be 0.025, shouldn't it? Aha.
0.15.
0.1. Wait.
Because we are dividing.
A quarter. Yeah. You're right. It should be What do I do with that? Yeah, you're absolutely right. It should be 6 to 3, so 0.15. Yeah, 0.15. Sorry, you're absolutely right. Error on my calculation. So let me go back to that. Give me a second. Go back and thank you, Amir. Try that again. Pen. Okay, so let's go back and do this again. So we've got 0.0500 right, liters times 6.00 moles of HCl per liter of solution, right, per liter. So those cancel. And then we go divide that by, so 2 moles of HCl per 1 mole of zinc. Yep. Yeah, you're right. So 3, so it should be 0.150 moles of zinc. Yeah.
Thank you.
Thanks. All right. So you take the 0.150 moles of zinc, multiply it by its molar mass. So moles of zinc, let's see, erase that. There, okay. And so the molar mass is 65.38 grams per mole of zinc. And you should wind up with something along the lines of 4.990 or somewhere around there. Grams. No, that's not right. Hold on. I got to change my math here.
9.8.
Thank you. Got to account for the error in my notes. Okay. So you have
9.8
9.8. Oh yeah, actually that's
9.81 for
9.81.
3 sig figs.
Huh.
Thank you.
Well, I had that part right in my notes, but I didn't have the. This is the problem with transferring everything online. Coming up with a new example. Sorry, guys. Thank you for keeping me online here. So grams of zinc. Whew. All right. Give me a moment. That's what that is. Okay. With that, so that gives us an amount of zinc that should react with that volume. I see what I did wrong, actually. My example's right. I just did it in a slightly different order. So here we go. Next thing. Let's do another example. Help if I can read my notes this time. So in this one, we've got nickel sulfide, which is insoluble in water. So it can be formed according to a certain reaction. So it's sort of a different way of asking the question. Right? This reaction gives you a net ionic equation according to this, right? But its molecular equation is written up here. So you can calculate the volume of a certain concentration solution, in this case of potassium sulfide, right? So that connects to the initial solution that's required to precipitate all nickel, right? So the idea here is when you say required to precipitate all nickel from, in this case, a solution, right, of nickel chloride. So essentially what you're saying here is this is a stoichiometric reaction, or in order to get a stoichiometric reaction, how much of that potassium sulfide do we need? And so for that, we're going to actually start with the amount of nickel that we begin with, because that's the volume and concentration data. So that gets us to moles. So that's going to be one of the tasks of getting there, right? Is really just using the volume and concentration to get to moles for the stoichiometry in solutions. So here we start with 0.0425 liters, right? Always convert that into liters when you're doing stoichiometry. And you have a concentration of 0.165 moles of nickel chloride per liter. Okay, and so this allows you to calculate the amount of nickel, and those cancel here. Should wind up with along the lines of 7.0125 with 3 sig figs times 10 to the minus 3 moles of nickel chloride. Okay. And then from that, once you know the amount of nickel chloride, you can now use your mole ratio of the nickel chloride to the potassium sulfide. Okay. And so you say 7.0125 times 10 to the, should be minus 3 molar. Or excuse me, moles of nickel chloride. Okay, use your mole ratio, 1 mole of nickel chloride for every 1 mole of potassium sulfide. Okay, and that will give you the number of moles of potassium sulfide. All right, so right, which will be the same value, right? A 1-to-1 ratio will be the same, right? So 7.0125 times 10 to the minus 3 moles of K2S, right? And again, that should have 3 sig figs there. Okay. And so once you know how many moles of potassium sulfide you have, you can use this concentration here. And if you divide by concentration, and so here you take that 7.0125 times 10 to the minus 3 moles of K2S, divide by the concentration. So we've got 0.655 moles of K2S per liter. And when you do that, you wind up with, because the moles of K2S and moles of K2S will cancel out, you wind up with a volume. And so you wind up with 0.01076 liters of that solution. And so for that, you can also just change that, since we have 3 sig figs, to I would generally change that to milliliters, so 10.7 milliliters. Right? Okay, how are we good on that one? Any questions on that? All right, we'll go on to our next example here.
Yes, question. Do you want the answer in liters or milliliters, or it'll depend?
If I specifically ask for it in liters or milliliters, then put it in that. Otherwise, just be reasonable, right? If it's in, if you're talking about, 10 to the minus 3 liters, just change it into milliliters. Just sort of use common sense on that, because that's the reason we learned all of those, the unit prefixes in the first place. But unless I specify, I'm really not looking, that's not something I'm specifically looking for. Okay, so our next example, all right, is another way of asking a precipitation question. And that's calculate how many grams of lead oxalate can be precipitated by mixing 25 milliliters of 2 molar lead nitrate with 40 milliliters of 1.5 molar potassium oxalate. The equation for the reaction is given here. So oxalate doesn't actually come in our specific list of solubility rules, but you can see from this particular equation, oxalate tends to be a polyatomic ion that is insoluble in many, many cases, at least cases with +2 ions generally. So what you can do here, you can use this particular reaction and the understanding that you have a certain amount, right? So you've got a certain amount, 25 milliliters of lead nitrate with that 2 molar concentration. And then you have 40 milliliters of 1.5 molar potassium oxalate. So in this particular reaction, you have moles of each of them. When you have moles of both reactants and you want to find out how much of a product you're producing, this is kind of a limiting reactant question, is you want to find that limiting reactant first. And then once you have the limiting reactant, based on the number of moles of product, you can calculate the grams of that product. So we want to figure out how many moles of each of these reactants we have, or how many moles of each of these reactants will produce a certain amount of a given product. And so when we're doing stoichiometry reactions or precipitation reaction stoichiometry and limiting reactants, what we tend to look for is going to be the how much solid can you make? How many moles of solid can you make in a given reaction? So we're going to start this with our 25 milliliters of lead nitrate. So for the lead nitrate, we've got 0.025 liters. Multiply that by the concentration, 2.00 moles of lead nitrate per liter. Okay, the liters are going to cancel out there. Okay, and then we'll put in here, just like we did with other stoichiometry limiting reactant questions, our mole ratio for lead oxalate. So 1 mole of lead oxalate will be produced for every 1 mole of lead nitrate. and you wind up with 0.050 moles of lead oxalate. Okay. And then we'll take and do the same thing for potassium oxalate. So we'll take this and say, okay, well, we've got 0.040 liters of the potassium oxalate. We've got a concentration of 1.5 moles of potassium oxalate per liter. Again, liters are going to cancel out. Multiply that by the mole ratio. Here it's a 1-to-1, so 1 mole of potassium oxalate for every 1 mole of lead oxalate. And we get a product, or a moles of product of 0.060 moles of lead oxalate. Right? So on this one, if we started with the lead nitrate, right? If we started with the lead nitrate here, that didn't work. If we started with the lead nitrate there, right, we made 0.050 moles of lead oxalate. If we started with the lead nitrate here, or excuse me, the potassium oxalate there, we made 0.6. So our limiting reactant, right, produces the smaller amount. So the limiting reactant, so I'm going to abbreviate that LR, is lead nitrate. Okay, and so we take that 0.50 moles, and we basically just multiply that by the molar mass of lead oxalate. And so 0.050 moles of lead oxalate. Okay. Multiply by the molar mass, 295.2 grams of lead oxalate per mole. And that'll give you the mass of 14.76 grams, right? Or in this case, with 2 sig figs, 15 grams of lead oxalate. Okay. All right, so there's sort of another way that these precipitation reactions can be asked. So sort of long story short here, we're describing these reactions and solutions, and now we're doing stoichiometry with them. The only big thing that we need to know is when you multiply a volume times a concentration, right, you get moles. If you divide moles by the concentration, you get a volume. If you divide moles by volume, you get a concentration. So it's just understanding the ins and outs of molarity and how that plays with either moles or liters of a given solution. And if you do that and make that small adaptation to your toolbox, then you're going to be able to do these precipitation reaction stoichiometry problems. Okay. So a little bit going on there, and so that basically takes care of.
I actually have a question about the limiting
Yes.
reactant. What's a good key word that we can look for when we're, oh, it's a limited reactant question or not?
So there's,
because it doesn't specifically ask.
That's right. But what it does ask you, so how many grams of this can you make, right? This isn't always going to be a very specific, hey, look for this word type thing. it's sort of more of an understanding of, okay, so you read the first part of it, you say, okay, I'm going to figure out how many grams of this product I can make. Well, I'm given now some amount of a reactant, okay? If I'm only given one reactant, then I know that that's going to be what defines how much of the product I can make, okay? When you have two different reactants, then you're going to have to say, oh, okay, well, I can only make so much from this one reactant, right? And I can make so much from this other reactant, right? So when we did that before with just masses, we said, well, how many moles of, say, water we could make from the combustion reaction of, 10 grams of methane with, 50 grams of oxygen or something along those lines, right? So this isn't quite as straightforward as just the limiting reactant, but now that you have two amounts of reactants, you should be able to sort of figure from that, oh, okay, one of these is going to be a limiting reactant, right? And that's sort of what should tell you. So it's not so much a silver bullet of what words am I looking for, so much as what types of things in a chemical reaction might lead me in that direction. Did that help?
Yes, thank you.
Okay, great. All right, so that's precipitation reaction. That's the first and really the most involved of the types of reactions that we're going to look at in chapter 4. The next thing that we're going to talk about is a little bit of acid-base reactions, which in this case, from our standpoint, we're going to look at them as neutralization reactions, okay? So an acid-base reaction, or in most cases, when we talk about acid-base reactions, we're looking at neutralization, which is basically when an acid and a base react stoichiometrically. All right, so if you have a monoprotic acid, we'll talk about monoprotic versus diprotic, and protons and all that. So if you have an acid has a hydrogen ion in it, right? That hydrogen ion will react with a hydroxide in general. And so if an acid has only one hydrogen ion, then it only needs one hydroxide ion. So that would be a 1-to-1 stoichiometric reaction if you have what are called a monoprotic acid with a base, okay? So in a stoichiometric reaction there, you have 1 mole of acid for every 1 mole of base, okay? That's the basic idea of a titration, is we're seeing stoichiometrically the same amounts of each of these things. So when we think about an acid-base reaction, we're really not looking at anything that's going to be a limiting reactant question. We're looking at equal amounts of the two reactants, and that's going to allow us to do certain things, okay? Now, we have a couple of definitions to look at, and we've really sort of explored of the definitions we've explored in the past. We've looked at the Arrhenius definition. We've done that a little bit in the past, where the whole idea of the Arrhenius definition, don't know why my pluses, my charges on these ions aren't superscripted, but they will be soon. So if you have an acid, the Arrhenius definition, which is the simplest definition for an acid. There are actually 3 definitions that chemists go by when it comes to acid-base definitions. We're going to explore 2 of them. If you go on to 102, you'll really look at the 3rd one a bit more in depth. For us, the first one we look at, the simplest of all of them, is the Arrhenius definition. And that's a substance, so when you dissolve it in water, it's going to produce a hydrogen ion, okay? A base, when according to the Arrhenius definition, right, is when you just dissolve it in water, it's going to produce a hydroxide ion. So for these 2 definitions, the acid must have a hydrogen in its chemical formula that will break apart or dissociate fairly easily. The base is going to be an ionic substance with a hydroxide, right? Okay, so that's going to be the difference between the acid and the base. One has a hydrogen ion associated with it, and the other one has a hydroxide. So that's really simple, but it limits you to solutions that are aqueous, okay? It also limits you on the base side of things to things that have hydroxide in the chemical formula. Now, a better example of a base for what, or an acid and a base for what we use is the Bronsted-Lowry definition, okay? Now, Bronsted-Lowry says an acid is a proton donor, right? And a base is a proton acceptor. And so understanding what a proton is the key, right? So a proton, and I think we've talked about this before, but a proton is just an H plus, right? Because a hydrogen atom is a proton and an electron. And then once it becomes an ion, right, hydrogen gives up an electron to become just a proton, right? So when we say a proton donor or a proton acceptor, we're talking about something that either gives off an H plus or accepts an H plus, okay? So those are our definitions of acids and bases, and we'll start to see those more and more and get more and more familiar with them. In a Chem 102 class, you get really familiar with them because there are multiple chapters that use acids and bases. There are like 3 chapters of acid-base chemistry in one way or another. The type of experiment that is done in acid-base or neutralization reactions is called a titration. So if you've had a Chem 60 class, you should have done a titration in the past. That's everybody's favorite, where you take a burette, so up in the top right-hand corner, right? That thing there is called up top is a burette, and that burette has, it's filled with either a base or an acid. Usually it's a base, at least for the reactions that we do in general chemistry, something like a sodium hydroxide solution. And you generally know that concentration of that solution. Then what you do is you have this known concentration of the solution in the burette, and you have an unknown concentration of a solution in the Erlenmeyer flask, but you know the volume of its solution. And so when you know the volume of the solution in the Erlenmeyer flask, and you know the concentration of the solution in the burette, you can add the base, in this case, to from the burette to the Erlenmeyer flask until it reaches neutralization, okay? And it reaches neutralization if we're using an indicator. So if you did the titrations in Chem 60, you used a phenolphthalein indicator, which turns pink at what's called the end point. And the end point just signifies that the reaction is done. If you picked a good indicator, right, it changes color when the stoichiometric equivalence point is reached. Now, again, that's something you won't need to know. It's too in-depth right now. If you go on to 102, you'll spend quite a bit more time with indicators then, and understanding how to pick a correct indicator for a given chemical reaction or given acid-base reaction. So the idea is it turns pink when you have that stoichiometric equivalent of base added to the acid. That allows you to calculate based on the concentration, right, of the base and the volume of the base. You already know the volume of the acid there. And so based on those things, right, multiplying the concentration times the volume of the base, and knowing the volume of the acid, you can, and the stoichiometry of the reaction, you can determine the concentration of that original acid solution. And so that's where titration is really useful in things like food chemistry, useful in some organic chemistry reactions as well. For example, food chemistry, oftentimes you want to know how acidic something is. In particular, one of my favorite places is the wine industry, where the acidity of a wine is important for the taste of the wine and how well that wine holds up over time. And so people will determine the pH of a given wine or the acidity of a wine by occasionally doing a titration. And so,
can I ask you a question, sir?
Sure.
Thank you. I actually have 2 questions. One is about it's a laboratory question regarding the picture that we have over here. Mm-hmm. This has been overdone, right? Like it has too much base in it because of the color, I'm assuming.
Yes. Yeah.
So that's not the color that we actually have to see. It has to be like the color that we see on the burette that is below it, right?
Yeah, so this, yeah, you're right. So when you've done titrations in like a Chem 60 class, if you went to a really dark pink, it was way past the endpoint. Now, this illustration, right, it's really hard to take a picture that's meaningful when it's really the lightest pink that it should be, because it's almost clear, it's so light. So the pink of a titration, even this down here where there's the sample reading of a burette, even that's too dark of a pink color for a given titration. Yeah.
And second question is about acid base. You said acid is a proton donor. Does it mean the more number of hydrogen that it has in its formula, it's basically stronger? As an example, is sulfuric acid stronger than hydrochloric acid?
No, that's not the case. And so that's something that you'll actually look at in 102. There are structural reasons why an acid is stronger or weaker. Those things are going to be things that it'll be easier to talk about once we look at bonding, because bond strengths for, in particular, covalent bonds. So acids are covalent substances, but they act in a very ionic way. And the strength of the hydrogen bonded to whatever element it's bonded to. In the case of sulfuric acid, hydrogen is bonded to an oxygen. In the case of hydrochloric acid, it's bonded to a chloride or a chlorine. And the strength of that bond is going to govern how strong of an acid it is. And so there are some very key structural elements to it that you really explore much more in depth in Chem 102 class. But it's something that we can come back to and spend a little bit more time on if we want to in chapter 8 and 9, once we start to see things that influence the strength of a bond. And in particular, once we start to really have a feel for electronegativities and polarity as a bond, that will help as well. Because things that will influence the acidity of something are things like the bond length, which is related to bond strength, and the electronegativity of the substance. But there are other things like resonance and things like what's the charge. So for example, hydrochloric acid and sulfuric acid in water are both considered what are strong acids. Okay, both of those substances and we're only going to mostly deal with strong acids in here. Both of those substances, when you put them in water, we consider them to dissociate completely, okay? Because they ionize completely. That's strong acids or strong electrolytes, right? And so when they both dissociate, they give off a proton. Sulfuric acid has 2 protons to give off, right? And so the 2 protons of sulfuric acid don't have the same acidity. The first one is going to be more acidic than the second one, and that's going to be largely based on some charge issues with the conjugate base, okay? So, which is something we'll explore a little bit as we move forward in acids and bases, okay?
Thank you.
For that one, but yeah, it doesn't have to do with the number of protons entirely, okay? All right. So, if we take and understand an acid-base reaction or a neutralization reaction as being a stoichiometric relationship, then or between an acid and a base, then what we really want to do is be able to say, okay, so if 10 milliliters of a strong acid is titrated with some volume of a strong base, so we're going to largely deal with these strong acids and strong bases because it's just a simpler way of dealing with things right now. Like I said, you'll explore it more in depth in a 102 class. But the whole idea here is if you know the volume of acid that you started with and you're titrating with a base, and you know based on, try that again, and you know based on the experiment that you've added 25 milliliters of the base with a known concentration. So you know this concentration of the base. The experiment gives you the number of milliliters, the volume of the base that you add, and you know the volume of the acid that you started with, but you don't necessarily know its concentration. And so you can figure out that concentration based on the stoichiometric reaction of the two. Okay?
Professor, this might be a dumb question, but in the book, there's neutralization reaction problems, and then there's acid-base tritation problems. Which one is this a tritation problem because it says tritated?
Yeah, so neutralization and titration are, for our intents and purposes here, they're pretty much interchangeable, right?
Okay.
A titration is a neutralization, assuming you stop at the endpoint.
Got it.
Yeah, in a Chem 102 class, you actually follow the titration past the endpoint as you use a pH meter to measure the acidity of the solution. And so you get different information about it from that. But yeah, we'll consider a titration and neutralization to be the same thing. So first thing we should always do when we see this is write down a chemical equation, right? So if you know that you've got a strong acid and sodium hydroxide, sort of a generic strong acid, would be something, we would write it out as HA. The H signifies there's a proton, and the A just says it's an acid, okay? And so what we can do here is we can say, well, HA, it's aqueous, plus sodium hydroxide, it's aqueous. They react. When they react, it's sort of the same idea as with the precipitation reactions, right? We're essentially swapping cations and anions, right? And so we would make, if we have the H and the OH, right? So HOH is another way of writing water, right? And so that'll be a liquid because it's an aqueous solution. So you don't write aqueous water, right? It's going to be a liquid because aqueous water would be redundant, right? You add, and the other product will be the sodium and the acid, the A minus. Now it's an A minus because it's an acid, it's giving up H plus. So this is H plus and A minus, right? So H plus and A minus over here, right? And so it makes sodium A, and that'll be aqueous. So what we're making here is we're making water and a salt. Not table salt necessarily, but a salt, okay? And in general, when we have a strong acid reacting with a strong base, that's gonna be a way of looking at this chemical reaction. So here, to figure out the concentration of the acid, first we need to figure out how many moles of the acid we started with. And so we can do that by taking the volume of the base. Oop, that's not right. Try that again. 0.0253 liters of base with a concentration of 0.1032 moles of sodium hydroxide per liter. Right, those cancel out. And then we also want to know the mole ratio of the two. In this case, if I tell you it's a strong acid, it's going to be monoprotic, or there's going to be one proton if you hear monoprotic. Okay, so we have 1 mole of HA for every 1 mole of sodium hydroxide. Right. And from that, you can figure out how many moles of acid there were in that original solution. In this case, 0.00261. That's a 6 moles of HA. And once you have that, you take the moles, so 0.00261 moles of HA, divide it by that original volume, right? And so you can set it up like this. Divide by that 10 milliliters up here, right? So only converted into liters, so 0.0100 liters will give you the concentration of 0.261 molar HA. Okay. All right. And so the other example we have is going to be for a diprotic acid, which we'll do tomorrow. We'll start the class tomorrow with that, and then we'll move on and talk about oxidation reduction reactions and get ourselves acquainted with Canvas. Okay. So
question about the lab. Is that a hard 8 a.m.? Like if it's, because you know, you have a late policy.
Yep.
So if we submit it at 8:01, is that considered late? Are you going to give it to like 8? Just I'm thinking like computer issues, internet issues, so on.
Yeah, so that's why so for this first day of lab is just the safety stuff, right?
I was talking about more the submitting.
Submitting stuff, yes. 8 a.m. it's a hard 8 a.m.
Okay.
Always come and ask questions then. What I will say though is, so after 8 a.m. it's considered late and the late policy applies. So if it's after 8 a.m. it's a day late. If it's, you know, after 8 a.m. the next day, it's a day late, it's 2 days late, etc.
Got it. Okay. Thank you.
All right. Mm-hmm. And these labs, once you start these labs, they shouldn't take you super duper long, right? And you can do them at your leisure. Like you can pause, you know, somewhere in the middle and you come pick it up again later. That's fine too. Yeah, Amir.
Do we have to use the long method answering these type of questions?
Do you have, hold on one sec. So I'm going to pause. I'm going to stop our recording here.